Hi everyone, Mr. Lee here. In this video, we're going to go over rotational kinematics and the calculus that goes behind it. So, before we start, I want to remind ourselves of the rotational version of the translational kinematics equation, such as x for position, v for velocity, a for acceleration, and t for time. Because right next to it, we have the rotational versions of the same variables. So we have theta for position, omega for velocity, alpha for acceleration, and t for time. And the reason I want to do this is because we're very much used to the translational variables, and so it might just take a little bit of getting used to the rotational variables, and I like to have it up so that you have a direct visual thing to compare it to. Alright, so what I'm about to do next is I'm going to create a table for you. We're going to create a table for the calculus behind the kinematics equations. So let's start off by labeling one of the columns the derivative. Okay, the derivative form, and we'll have the integral form. All right, and then we're going to have the position. We're going to have velocity, and we will have acceleration. Okay, so what I want to do is I'm going to start off with the velocity. So if you want to find the velocity, okay, if you want to find velocity, we often say velocity is the derivative of the position function with respect to time. Right? So vt is equal to dx over dt. So if you have a position function, so such as x of t, if you take the derivative of it, you can find the velocity. Right? And from there, let's go to the acceleration. So for the acceleration, if you have the derivative of the velocity function, you can find the acceleration. Or if you take the derivative twice of the position function, you can find the acceleration. So there's two ways that you can find acceleration. Okay, and position is just going to be position, which we can call it just x of t. All right, you can't get there from deriving anything. All right, now what about the integral form? So the way I like to imagine the integral form is like the reverse of the derivative form. So if I have a velocity function, okay, if I have v sub t, I can go from velocity to position by taking the integral. All right, so I'm going to say that again. If I have a velocity function, I can get to the position function by doing the integral. And the reason for that is because if we had a position function such as dx, or excuse me, if we had a position function such as v sub t, x sub t, we could get the velocity by taking the derivative. So the opposite of it would take you backwards. And so we can say x of t is equal to the integral of the velocity, or the integral for the velocity function with respect to the time. Okay, and we go from usually from time 0 to time final t, like so. All right, so we can see how here the velocity function here is, if you take the integral of it, you get the position. Okay, so it goes forwards and backwards. Now, with that being said, if I wanted to find the velocity function and I'm given a acceleration function, because finding the derivative of a velocity function gives me the acceleration, the reverse is true. If I want to find the velocity function, all I have to do is I have to take the integral of the acceleration function from usually from 0 to whatever time t. Okay, and that is just the acceleration function. Okay, all right. So if we have this in mind, this table in mind, we can find the rotational versions of this table. So what I'm going to do is I'm going to create a line here. Okay, and on my right hand side, it's going to be all of the rotational versions of this. So for derivative, I'm going to write d and I for integral. So the rotational position is going to be theta with respect to time t. Oops. Yep, there we go. Okay, and so here we see that the integral form is x of t. So instead of x of t, I'm going to write theta of t is equal to the integral of 0 to t, where instead of v for velocity, I'm going to write omega dt. Okay. Here for velocity, instead of v for velocity, I'm going to write omega for velocity. The function of omega with respect to time is equal to the derivative of the position function with respect to time. And instead of saying x for position, I put in theta for position. And of course, the integral would be omega t is equal to the integral of 0 to t. Instead of a for acceleration, I'm going to put alpha dt. Right? And the very last one down here, instead of saying a sub t, I'm going to say alpha sub t is equal to the derivative of the velocity function with respect to time. It's also equal to the derivative taken twice of the position function with respect to time squared. And this is also alpha sub t. Right? So here you can see all I did is I took the derivative forms and I replaced the variables that are translational, and I replaced it with the rotational variables, as we can see in this table here. Okay, and so until you get used to this, I do suggest that when you see a problem that you use the translational ones, but at the end you can substitute it with the rotational ones until you become familiar with the Greek forms of the variables. All right, now let's try a practice problem, shall we? This practice problem, I'm not going to give you any numbers. We're going to try to do everything in variable form, because if you can do it in variable forms, you can do it with numbers, because all you got to do at the end is just plug in the numbers, right? You got to just plug and chug. All right. Now, the scenario that I'm going to give you, let's say it's a circle, right? It's a disc, and this disc is rotating and spinning around. Whee, right? Spinning around and around. And the acceleration of this object can be given with the following function. Alpha sub t is equal to negative capital A omega squared, where A is just a constant, it's a number, and omega is, of course, the velocity. All right, and here's what we know about this item. It has the initial velocity of omega initial. Okay, and we start off at time t is equal to 0, and we end at time t of capital T. All right, and what are we looking for? Well, we're looking for the final velocity. What is it? Well, we're about to find out. Okay, so we're given this problem here. And what you need to be able to do is we got to take a look at this, and we got to be able to successfully be able to use the calculus in order to come to the final conclusion. Let's go to that chart that we just made. So if I look at this chart, okay, let's take into account of what we are given. So what I mean by that is you should always know what kind of function you have. So the given function, we have a alpha with respect to t, right? And what do we want? We want the omega final. So we want to go from alpha to omega. Okay, we want to go from alpha to omega. And so if we take a look at the chart here, we can see that I'm gonna highlight this right here, that this right there, that describes what we need to do in order to go from alpha to omega. Because we're given the alpha function, and in order to go to the omega function, what we got to do is we got to take the integral. We got to take the integral of the alpha function. So let's do that, shall we? All right. Ba-ba-bum. Now we're gonna do some wild kind of calculus. So buckle yourselves in. Line. All right. If I know that this is my function, okay, we can't just go straight into it. We can't just take the integral of this. It just doesn't work that way, because, well, we gotta take a few extra steps. So instead of saying alpha function of with respect to time, what I'm gonna do is I'm gonna use the alternate definition of alpha, which is d omega over dt is equal to negative a omega squared. And the reason why I want to do that is because the original function has omega in it, right? So we gotta have like terms. Now, speaking of like terms, I gotta combine the like terms together. I gotta have all the like terms over on one side. So if I take a look here, I see that there's omega on my left, omega on my right. I don't like that. I want to make sure all my omegas are on one side. So what I'm going to do is I'm going to divide both sides by omega squared. Okay, and so if I do that, I get d omega over dt divided by 1 over omega squared is equal to negative a. Looks pretty good. However, look at this dt. Does not belong there. Dt does not have an omega attached to it, so I'm going to move dt to the other side by multiplying both sides by dt. So we get negative a d sub t is equal to 1 over omega squared d omega. Okay, so right now all we did is we set up the function so that we can now properly integrate it so that we have all the like terms together. Okay, so what I'm going to do after this dotted line, right, so everything above the dotted line is just a setup, and now I'm actually going to do the calculus behind it. I'm going to integrate it. Wow! So if I integrate both sides, right, I create that fancy integral symbol, I need to be able to set the terms, right? I have to set the conditions, the initial and the final conditions. And I personally find that a lot of students have difficulty with doing that. What is my initial and what is my final? And so my clue to you is to just take a look at what is the d, right? The d variable. So here we have d omega. So that tells you what your constraints are. My d omega initial, or my omega initial is just my omega initial, and my omega final is just my omega final, right? Those are my variables. That's how I am integrating. I'm going from your initial velocity to my final velocity. So if I take a look over here, we have dt. Well, that was simple. My initial time was just 0, and my final time was t final. I believe the problem said is just capital T. Okay, so I set the conditions based on the variable that is attached to the d. So that's my quick little tip for you. All right, what do we do next? Well, we got to integrate it. So here, what I'm going to do is I'm going to, for the sake of making this a little bit cleaner on my eyes, I'm going to make this, instead of omega squared in the denominator, I'm going to make this omega to the negative 2. Okay, so that I have everything all in one line. All right, so if you remember, the integral is like the reverse of a derivative. Okay, where the derivative, we took the exponent and we subtracted it by 1. For the integral, we do like the reverse. Right? So what I'm going to do is I'm going to add 1 to this exponent. So we get omega negative 2 plus 1. So we get omega negative 1. And my conditions are going to be from omega initial to omega final. Right? But there should be a negative here. And that negative 1 that comes out in the front is from the power rule. Right, we always put in front of it the n plus 1, right? We put the exponent in front. Okay, so on the other side, I'm going to show you another thing that I find a lot of students get a little bit, with trouble. Here, the only thing that we want to keep on the right-hand side of the integral is the variable that we are integrating, and in this case, it's time. Now, this negative and this a, that has nothing to do with time. That negative is just a constant, negative 1, and that a is just a number. It's a constant. Has nothing to do with time. So we're going to bring it out to the front. So I'm not even integrating just yet. So we have 0 to t dt. We have something that looks like this. All right. Now, from there, I can integrate it because that dt has time in it. So here we have negative omega to the negative 1, omega initial, omega final, and the integral of the dt simply becomes t from 0 to t, and that's one of those special rules. Okay, all right. Now at this moment, we're almost there. What we got to do is we got to plug in the constraints. So it'll be negative omega final to the negative 1 power minus negative omega initial to the negative 1 power is equal to negative a to the capital T minus negative a times 0. Okay, so we put in our initial and our final conditions there. All right, so now we got we got negatives all over the place. Let's clean this up. So this negative and negative, that becomes a positive. So negative omega final to the minus 1 plus omega initial to the minus 1 is equal to, well, this is just 0, right? A times 0 is just 0, so we get negative AT. All right, so we have negatives all over the place. What I'm about to do now, because we're looking for omega final, okay, and there's a negative that's in front of the omega final. We don't want that negative there, multiplying everything by negative 1. So we get omega final to the negative 1 minus omega initial to the negative 1 is equal to AT. So I just reversed the signs of everything there. And because we are trying to find omega final by itself, we're going to put omega initial on the other side. So we get omega final to the minus 1 is equal to AT plus omega initial to the minus 1. All right, we are almost there. You might be thinking, Mr. Lee, we found omega final, right? But technically we didn't, because this actually looks like this, right, to the negative 1 power. Okay, so we actually didn't find omega final. So we need to do something with that negative 1 power. Let's see what we can do. All right, home stretch. So we have a inverse here. So mathematically speaking, in order to invert something that has been inverted, all you got to do is invert it, right? Okay, and so what that means is I just can take the negative 1 power to everything. I am inverting the inverted. So this function will be inverted there, and here we're going to invert everything here. And so what ends up happening is our final answer will look like this. Ta-da! But that doesn't look clean at all. So we're about to clean that up. But technically that is our final answer. So if I were to clean this up, I would say, because this entire thing is inverted, that is 1 over AT plus omega initial, which is to the negative 1, which is just 1 over omega initial. And here we have a fraction within a fraction, and we don't like that. And so if we were to simplify that, we would get omega initial over 1 plus AT omega initial as our final answer. All right, so this is our final answer. This is a tad bit cleaned up, and this is like the cleanest version of our answer. All right, so that is that. Wow, that looks impressive, doesn't it? Put that on your fridge. Just slap it on there with a magnet. This is rotational kinematics with calculus. The important thing is that you're able to go from the translational to the rotational variables, and it's important to know how to properly take the integral by the different functions that they give you. See you next time. Bye-bye.